Up to this point, when we've done integrals, we haven't had any special rules. If you remember, we pretty quickly had to learn with derivatives the product rule and the quotient rule and the chain rule in order to be able to do very many at all. Well, we haven't really learned any of those yet, but today's the day. We're going to be talking about u-substitution, and it is basically the reverse chain rule. Or you could call it the chain rule for integrals. Let's really quickly just kind of remind ourselves what the chain rule looked like. So for example, if we had f of x equals x squared plus 2x to the fourth, when we took the derivative, we did the derivative of the outside, which was that exponent of 4, gave us 4 times x squared plus 2x cubed, and then we would multiply by the derivative of the inside, which was 2x plus 2. Or if we had a trig one, like cosine of 4x plus 1, we'd do the derivative of the outside, that would be the cosine. Derivative of cosine is negative sine. And we would multiply by the derivative of the inside, which would be 4. So again, that's just a brief review of what the chain rule did and how it looked like. Okay, now for integrals, like I said, this is called u-substitution, and it's probably the most powerful rule and the most useful rule in all of the integrals. There is kind of a reversed product rule, but we won't touch that till next semester, and it's significantly more complicated. But u-substitution is pretty straightforward. So let's just start with an example, and I'm just going to show you exactly how it works. We're going to do the integral of x squared plus 1 squared times 2x dx. Basically what's happening here is we're going to try to rewrite the function in a way that makes it easier for us to take the antiderivative. Because as it is right now, it's pretty difficult to see how that would work. So here's what you do. The first thing you need to do is pick your u. Now your u actually corresponds to the inside equation that we talked about when we were doing the chain rule. So what you need to look out for is things that are inside of powers, inside of radicals, inside of trig functions, or inside of denominators. So that's what you want to look for, and that's what you want to pick for u. So in this case, it would be x squared plus 1. So over here to the side, I'm going to write that u is equal to x squared plus 1. And then I'm going to take the derivative of u. And that's going to give me 2x dx. Now I know we normally don't write that dx, but for the u-substitution it's necessary. Because here's what we're trying to do. We're trying to line up all of the pieces on the right side with pieces on the left side, because we're going to substitute. That's why it's called u-substitution. So if you notice, those are a perfect match. Let me go ahead and extend the page. There is a perfect match there. I can replace x squared plus 1 with u. So instead of x squared plus 1 squared, I now write u squared. And I'm going to replace all that 2x dx with du. So it's just substituting, because I said du equaled 2x dx, so I'm just going to replace 2x dx with du. Now if you look, that looks like a really simple antiderivative, and it is. You just add 1 to the exponent, and then you divide by that number. Don't forget plus c, because since we don't have any boundaries on this one, we've got to put plus c. Okay, well we can't leave it in terms of u because we didn't get it in terms of u. So there's just one last step, and that's to plug in what u equals. Well, if you go back up here, u is equal to x squared plus 1. So I put x squared plus 1 back in for u, and this is my final answer. And if you wanted, you could actually check yourself. If you were to go back and take the derivative of what we just found, your result would be this up here. So you're welcome to check yourself on that if you want to. I don't think you necessarily need to do that every time, but you certainly could do that as a way to check. Okay, now let's do another one. Let's do x times the integral of x times x squared plus 1 cubed. So for these, the first thing you need to do is try to figure out what you should use for u. U would equal x squared plus 1. Again, you want to look for something that is inside something else, because u is corresponding to our inside piece. So this would be x squared plus 1 again in this problem. Now I would take the derivative, and it would give me 2x dx. Alright, now we've got a little wrinkle here. We've got a little issue, because last time our u and our du matched up exactly. But this time they don't quite. First of all, x squared plus 1, x squared plus 1. Alright, that should always match because you picked the u, so it better match. But this is not got quite a match. Now, x and dx aren't together this time, but that's not a problem. We're multiplying, so we could rewrite that with x dx next to each other if we want. But x dx is not what we have over here. We have 2x dx. So think about this just like you're exchanging money. If you're told du is worth 2x dx, you're not going to be willing to trade it for just 1x dx, which is all we have over here. So what we need to do is rewrite what we have so it matches. So I have 2x dx, I need it to say just x dx. So I very simply just divide both sides by 2, and I get that 1/2 times du is equal to x dx. Now we do have a perfect match. I have x dx over here, and I have x dx over here. So I can trade them in. So now I'll go ahead and substitute what I see. I'm going to put x squared plus 1 as u, and x dx as 1/2 du. Okay, so that's it right there. Now, just so you know, you're multiplying, so you can put things in any order you want. I would always put the coefficient out front and the du last. That's not more correct than doing it another way. It's just the way I would recommend, because I think it keeps it simpler. So no matter where the pieces are that you're substituting for, I would always put the coefficient out front and the du last. Okay, so now this looks like a much simpler derivative right here than it did when we started. Much simpler. So I add 1 to the exponent, makes it u to the 4th, divide by that, so I get a 1/8 out front because I'm doing 1/2 divided by 1/4, plus c. My last step is then to plug in what u is equal to, get it back in terms of x, and that is my final answer. A lot of people ask a really good question here, and that is, what happened to my du? Where did it go? It just disappears. Okay, well, there's a couple ways to answer that. I think the simplest is actually to go back and look at the chain rule. Okay, if you think about it, we said we were calling u the inside piece. So if you look at this one right here, we could just rewrite this as u to the 4th. And when I take the derivative, it becomes 4u cubed times du, the derivative of the inside. So if you notice, when you take the derivative and you go that direction, the du just appears. It wasn't there before. So it should make sense that if you take the derivative and du appears, then when you take the antiderivative, du is going to disappear. So that's why du disappears. It kind of folds itself back into the problem. Okay, so let's move on and look at some more examples. Let's do the integral of x squared times 2x cubed minus 4 raised to the 6th. We're trying to choose a u. The key is to find something that is inside something else. So I'm going to choose 2x cubed minus 4, because that's inside that power of 6. Now I'm going to take the derivative of that. Derivative of 2x cubed is 6x squared minus 4, so that just becomes 0. And I always put dx with it, because I want to be able to substitute for that. We know derivative of x is just 1, but we've got to put that there anyway. Alright, so that's my derivative. So you see again, we're not matching up. Sure, the u matches, because it always should, but there's not quite a match with the du part. because all I have in my problem is x squared dx, and according to this, du is 6x squared dx. So just like last time, the answer is to divide both sides by 6. Now we have a match. Now what we have is equal to x squared dx. So plug that in. You're going to get 1/6 times u to the 6th du. I'm going to take the antiderivative, so I add 1 to the exponent and divide by that number, because I do 1/6 divided by 7. Then I add c to both sides. My last step, plug that u back in. Okay, so we've kept things pretty straightforward so far. We've just dealt with polynomials being multiplied by each other. So now let's ramp it up a little bit, and let's look at one that has a fraction. So let's say we have the integral of negative 4x over 1 minus 2x squared squared. We need to choose u. Well, it should be doubly obvious this time what to choose for u, because it's not only inside of the squared power, it's also in the denominator. So that's two good reasons to choose that as our u. So I do 1 minus 2x squared, and then I take the derivative of it. The derivative of 1 is 0. The derivative of negative 2x squared is negative 4x dx. So this one actually does match exactly again. If you look, negative 4x dx, negative 4x dx. Okay? So when I substitute, I get du over u squared, because I replaced negative 4x dx with du, and then I put u in for 1 minus 2x squared. Just so you know, if you would rather write this as 1 over u squared du, that's completely fine. It doesn't matter either way, whether you want to put the derivative or the du on the top of the fraction or out to the side. Same result either way. We do need to rewrite this, though, before we take the antiderivative. Bring that u squared up top as u to the negative 2. Then we're going to add 1 to the exponent and divide by that number. And don't forget plus c. Our last step is to plug our u in. Well, let's see, our u was 1 minus 2x squared, so we get negative 1 minus 2x squared to the negative 1 plus c. It's completely fine to leave your answer that way. Just keep in mind you could also move the whole thing back to the bottom. Like that. Either way is fine. Okay, getting there, just two more examples. We're going to try one with a radical. Let's do the integral of x squared times the square root of x cubed minus 2. Again, choose the u that is inside of something. So in this case, it's inside of a radical. So I'm going to choose u equals x cubed minus 2. The derivative of x cubed minus 2 is 3x squared dx. Don't forget to put that dx. It's important. You need to put it there. Okay, now we don't have a match this time. We don't have a match. Du does not quite match what we have, and we need it to. We got to get rid of that 3, so we divide both sides by 3. We get 1/3 times the integral of the square root of u du. Okay, you notice I pulled the 1/3 all the way out front. That's fine too. If you'd rather just keep it inside the integral, that's okay. So, like I said, you can write it this way, or if you'd rather keep it this way, same thing either way. So we need to rewrite this. In fact, I'll go ahead and put it back inside. Remember, that's one of the properties that you can move a coefficient in front of the integral or back inside, either way. Square root of u is the same as u to the 1/2. So now I add 1 to the exponent. Makes it 3/2. Then divide by that number. It's the same as multiplying by 2/3. So I get 2/9. Then I add plus c. My last step then is to plug back in for what u equals, and that was x cubed minus 2. That would be our final answer. Okay, last example. We're going to look at one that has a radical and a fraction. Okay, so to choose u, you look for what's inside something, so that would be 2 minus x cubed. The derivative of that would be negative 3x squared. So we don't quite have a match. Okay, look, this is negative 3x squared, and this is x squared dx. So we got to get rid of that negative 3 before we trade it. So we divide both sides by negative 3. Now we're ready. So I get negative 1/3 times the integral of du over the square root of u. Remember, the square root of u is the same as u to the 1/2. And then if you bring it up top, it's u to the negative 1/2. So that's how you should rewrite it. And then you take the antiderivative. You add 1 to the exponent. You can get positive 1/2. Then you divide by that number. Dividing by 1/2 is the same as multiplying by 2. So we get negative 2/3 u to the 1/2 plus c. Final step. Plug back in for what we set for u. Just so you know, it's completely fine to leave your answer like that, but it could also be rewritten with a radical. Both of those would be correct. Alright, very good. Hopefully that helps. The homework for this section is to do page 297, number 10 through 30, even.